Welcome to Organic Chemistry lecture series. My name is Isioma Ikhile, and today we'll be going over stereochemistry. Stereochemistry is the 3D relationship between atoms in the molecule in space. For example, so this is the structural formula of alanine, an amino acid. As you can see, this is like the typical way you would draw a structural formula. You can't show this in space. However, this is the 3D structure of alanine. So you see this cannot necessarily be represented by this, because this is, you see this is behind this and this is like directly in front of it, and these two, the amine and the carboxylate, is adjacent to each other. So this is the amine group, this is the methyl group, and this is the amino group. Like I said before, the reason why this cannot represent this very well is because this hydrogen is like directly behind the carbon, and the methyl group is like in front of it, and the amino group and the amine group and the carboxylate group is adjacent to each other. So, in other words, but there is a way you can represent this, like this. Since it's adjacent to each other, you just use the normal bonding thing, the normal bonds. But because this amine group is like this methyl group is like right in front of the carbon, you use a wedge to represent that. So it becomes this. So whenever you see a wedge, you can see that you automatically infer that it is right in front of it. While the hydrogen that's behind it will be represented by a dotted line. This is because it's like right behind it. So when you see a dotted line, you can infer that it's right behind it.
Okay, this is alanine. Let me describe the 4 connections. The 4 connections are carbon, double bonded to an oxygen, single bonded to oxygen, single bonded to hydrogen. This is a carboxyl group. Nitrogen, single bonded to hydrogen, and hydrogen by itself, and a methyl group, carbon bonded to 3 hydrogens. Now you could see that the amine group and hydrogen are on the plane. This is adjacent to each other. The carboxyl group is facing me. The methyl group is pointing backwards. Now, if we want to assign priorities in order to give it a configuration, figuring an R or S configuration, we will proceed by making some adjustments. There is a convention that is supposed to be followed. There's rules that we follow in giving a particular stereo isomer a configuration. Because we know it has a stereo center, and we know that it's a stereo isomer because the groups is connected to 4 different groups, so it has a mirror image. Now, I will turn it. The rule is that you turn the molecule so that the R is at the back. So now the R is at the back. I mean, the hydrogen is at the back, I meant to say. Now, which one has the highest priority? Of course, we know that nitrogen has a higher atomic number than the rest of them. 2 of them are carbon. So give you number 1, We give this number 2 because the carbon is attached to oxygen. This is attached to hydrogen. At the first point of difference, it's oxygen. First point of difference here is hydrogen. Now we're going to number it this way. This is number 1. This is number 2. This is number 3. The direction my hand is going is anti-clockwise. That's an S configuration. Only because the hydrogen is pointing at my back. It's an S configuration. Also, another way to look at it is turn it. You see how I flipped it downwards. I didn't rotate it. I just maintained the position, but flipped it downwards and look from the top. And when you look from the top, you're going to get a Newman projection, which I have shown you. You're going to get a Newman projection. And that will help you to disregard the hydrogen so you can focus in giving these a priority. So this is how it's going to be. In the paper, it's going to look like this. Because it's down, everything is going to be projected. So when it's down, all the groups are looking at you. That's the Newman projection. It's not going to change anything, even whether it's here or here. You see that the imine group is still maintaining the same side it was where it is. Like when it's here, it's on top. This is still on this is down, but the same position, relative position. The methyl group is on my right hand side. The carboxyl group is on my left hand side, and they remain that way. So the sense of rotation, it remains. It's going that direction. It's still maintained. But that helps us in naming this molecule. So now another thing I want to tell you is that when you turn, no matter how you turn this, no matter how you turn it, the priority remains. No matter how you turn it, it's definitely going to be 1, 2, 3. It's still going anti-clockwise, no matter how you turn it. But if the hydrogen is pointing towards me now, you see the rotation, the order will change. Let's see. This is number 1, this is number 2, this is number 3. So there was an exchange of positions. Number 1, number 2, number 3. So it has changed direction. Now it's going clockwise. And that's an R confirmation. Only if this was at the back. But because this is in the front, we're not going to call it R, we're going to call it S, because the rule is that the hydrogen has to be at the back.
Handedness is the tendency for you to use either your right hand or your left hand over the other. So basically using your hands at different levels. So if you notice your hands, you can't overlap them. You totally cannot overlap them. They look totally different when you overlap them. But if you look at your right hand, it's basically like a mirror image of your left hand. So that makes them chiral. Your hands chiral. For example, these compounds. What makes them chiral? These compounds are chiral because they cannot be overlapped. You see, they're different because this one is red and green, while this one is green and red. So, but if you look at this, if you put this one in front of the mirror, this is exactly what you would see in front of the mirror. So that makes them chiral. And although they do have different biological functions. And chirality is the property for an object to not be identical, or an object to not be identical to its mirror image.